Alright guys, how's it going? I hope y'all are doing okay. For this upcoming week, we are finally done with 9.5. And by now you should feel pretty comfortable with the polar coordinate system, how to plot points, what some equations look like. So this week we're going to focus on graphing. There is a whole lot of graphs that you can do in polar, but here in this class we're only going to focus on quite a few of them. We're only going to focus on, there's a few graphs we're going to talk about. We're going to talk about circles. We're going to talk about something called, and I hope I'm saying this right, it's called a limison. And we're going to talk about something called roses. And I mean, there's others that we've done in the past, but this year we're only going to focus on these three. So let's go ahead and get started, and let's talk about circles, which is the simplest of them all. Okay, so by now you're aware that there's no longer an x and a y axis. We are now dealing with the polar coordinate system, which means we only have your pole. Remember, we got a pole. So here's a attempt at a polar system. So we got a pole here, remember that. And then it is a coordinate system that is full of like a whole bunch of circles, etc., etc. Remember that each circle could represent one unit, etc., etc., right? Okay, so let's start out with circles. Now there's two types of circles that we're going to talk about, or two types of equations that we're going to talk about. The first type of equations are going to be in the form of r equals 2a. So, I mean, it's pretty simple. Think about it. Remember that r in polar mode, it really just means radius. So, really what it means is that this is a type of circle where the center is at the pole, and literally a would be the radius. So in other words, if you get something, for example, such as r equals to 2 and you're asked to graph, well, first, I mean, on WebAssign you're going to have some grids, or it's more than likely going to be multiple choice. But if you were going to do this by hand, let's call that 0. And I'm just going to say that I'm not going to draw every circle here, guys. It's going to take me forever. So I'm just going to say each square is like one radius out. So it's very simple. If they're telling you that r equals 2, all you got to do is go 2 in each direction. So that's what I typically do: 2 to the right, to the left, 2 down, and then you connect them, and you've got yourself a circle. So very, very simple. Again, this is the easiest type of circle that you can get, where r is just equal a number. You're not going to have anything else. It's not like you're going to have a plus something. It's literally just going to be r equals a number. Now, you could get something in the form of r equals negative 2. Now, that doesn't change anything. It's still going to be this exact same circle. Here's the difference, guys. It's just the way that it graphs itself. Remember that if you were to grab negative coordinates, for example, let's say that this, we already know that this angle right here, so this point right here would be 2 comma pi over 4 in polar. Well, this point could also be negative 2 comma 5 pi over 4. So if you were graphing this, when you wanted to plot the point for 5 pi over 4 for negative 2, it would have to be here. So at the end of the day, as you continue to plot the points, which at this point I don't recommend that you start making a table, it will give you the exact same circle. Okay, so I don't feel like this one's a very difficult problem. I don't think you need practice for this, but circles in the form of r equals a number. It's literally a circle whose center is at the pole with a radius of that number. Okay, all right. Other types of circles, actually, there are more. So we have another type of equation, and we have the equation in the form of r equals a cosine theta and r equals a sine theta. If you have equations of that form, that means that you're also dealing with a circle. So this is a circle as well. Now, things have to change because at this point, we can no longer be centered at the pole. Otherwise, it would just have to be r equals a number. So let's kind of investigate a little bit of what happens here. So let's come up with an example. Let's say that we have r equals 2 cosine of theta. Okay, so we're going to do our best here. Here's my polar coordinate system. and we're gonna see what happens. Now we're just gonna use our unit circle. We're gonna use our knowledge of the unit circle and see what happens. So remember that when you're plotting points, all you really have to do is just plug in angles into the equation and you'll start figuring this out. Okay, so first angle that we can plug in, let's start out with, let's go 0 degrees. Okay, so if you plug in 0, the cosine of 0 is 1, 1 times 2 is 2, so that'll be about right here. We have a point right there. Okay, so now let's see, what about if we plug in pi over 2? Well, the cosine of pi over 2 is 0, 0 times 2 is 0, so that will give us this point right here. If I plug in pi, all right, cosine of pi is negative 1 times 2 is negative 2. So that means pi is over here. But if I get negative 2, that means I want to plug in opposite of it. So that brings me right back to this. Interesting. So then if I plug in 2 pi, cosine of 2 pi is also 1. 1 times 2 is 2. So that will give me right here. Oh, I missed 3 pi over 2, right? Cosine of 3 pi over 2 would be 0, so that gets me back here. So what it really seems is like is I'm going back and forth, back and forth, back and forth. So I mean, I already told you this is a circle, so we can kind of use that to our advantage. If you really wanted to, you can plot in some other points, but really what it looks like is I'm going to have a circle, and I'm going to do my best, whose radius, by the look of it, is going to be 1 unit. So maybe about right there, and here's what it looks like. Cool? So we can start making some predictions as to about what this is, okay? For example, looking at the circle, what can you tell me then about the letter A? Well, the letter A, when I look at it, I mean, it's 2. When I look at the circle, it seems to represent the diameter. Now we have to, okay, awesome. Well, this was a cosine example. Let's see what happens with a sine example. Let's see, r equals 2 sine theta. Okay, so I'm going to do another coordinate grid here. So here's my polar grid, and we're going to do the exact same thing we did previously, which is just plug in values, and I'll try to use a different color here. All right, so if I plug in 0, the sine of 0 is 0, so that's going to give me a point right there. Okay, if we plug in pi over 2, so that's up here, so pi over 2. So sine of pi over 2 is 1, 1 times 2 is 2, so that'll be up here. If I plug in pi, sine of pi 0 times 2 is 0, so that brings me back here. 3 pi over 2, that would be negative 1, times 2, that would be negative 2. So at 3 pi over 2, which is down here, instead of going towards it, I'm going to go away from it. So I think by now you get the hang of it. We're going to have a circle up here. Now, how did I know to go just 1 unit this one? This way, remember, this represents diameter. So if the diameter is 2 units and the radius is 1, and we call this the center, then we're going to go 1 unit to each side. So once again, I mean, we've proved that A is the diameter, so diameter is 2. But let's take a look at what happened. Here's cosine, and here's sine. Think about the unit circle. On the unit circle, cosine represents what we call our x. Remember that? And sine represents what we call our y coordinate. Well, notice how when I graph the cosine circle, it seems to be to the right on the what you would call the x-axis. Right? We don't have an x-axis in the polar coordinate system, but we can kind of pretend for this moment. Notice when I have a sine, it looks like I have a circle with symmetry with what you would call the y-axis. So I think we can assume then that when it's cosine, you're going to have a circle whose diameter is going to be part of the x-axis, if we had one, and when you're dealing with sine, you would have one on symmetry with respect to the y-axis. Now, one last thing I want to comment is what would happen if I throw a negative in front of this number. So what would happen if I throw a negative in here and a negative in there? Well, let's go back and investigate on the graphs that we already have ourselves here. So I'm trying to grab a different color here. So let's use the same angles that we were using. So this time, cosine of 0. Cosine of 0 is 1. 1 times negative 2 would be negative 2, which would mean that I would have to be, at 0, I would have to be negative 2 units, so that would be about right here. If I plug in pi over 2, that still gives me 0. If I plug in pi, cosine of pi, that's going to give me negative 1. Times negative 2 gives me 2, so if I go towards pi 2 units, that gets me here. So I think you guys should get what's going on. We're going to go bounce back and forth, which means it gives us a circle that would look something like this. So we can deduce then that if we have a positive, so if I get rid of this negative, it was positive cosine, then we have a circle that is to the right of the pole, with a diameter of A. But if we have a negative, then I have a circle that is to the left of the pole with a diameter of A. So by that assumption, we should then be able to say that if I have a -2 sign, then that would mean that I would have to have a circle like this if it's negative. So let's go ahead and recap to make sure that you understood before I give you an example for you to try on your own. So we said, let's go ahead and recap, that when you have equations in the form of r equals, and it could be plus or minus cosine theta, or r equals plus or minus a sine theta, a is your diameter, and if it's cosine, it's going to be either to the left or to the right of the pole, and if it's sine, it's either going to be up or down. And to determine that, it's left for cosine is going to be left if it is negative, and it is going to be to the right if it is positive, and for sine it is going to be to up if it's positive and down if it's negative. So I want to go ahead and give you opportunity to try this. So if you have a moment to pause the video, give it a shot, and then hit play. Let's say you have something like r equals -3.5 sine of theta. So go ahead and pause your video, give it a shot, and when you're ready, just hit play. All right, I'm assuming you're giving it a go. So let's go ahead and go over that problem. So let's go ahead and draw our polar coordinate system. So by the look of this, we have a sine, which means that it's going to be, and we know it's a circle because it's in the form of r equals a sine theta. Sine is negative, so at that point I know I have a circle that's below, and I know that it has a diameter of 3.5. So at this case, we're going to say 1, 2, 3.5. And I'm going to do my best here. I'm not going to be perfect, but it looks like I have a circle. Oh, that's a terrible circle. That looks something like that. Okay? All right. So that's circles for you. The next thing we are going to talk about, it is going to be Rose curves. So Rose curves. Rose curves have the form of r equals plus or minus a cosine and theta, or r equals plus or minus a sine and theta. Now, there's something peculiar about this, where n has to be greater than 2. Okay? Now, let's talk about why that is true. Well, first of all, if n is equal to 1, then that would just be a circle, and we just talked about that. If n equals to 2, actually, I'm sorry. It's not greater than 2. My mistake. It has to be greater than 1. I was thinking about something else. My apologies, guys. It has to just be greater than 1. Because if it is greater than, like I said, if it is 1, then you're gonna have a circle. Okay. So let's talk about what these things look like and some strategies that I can give you in order to graph this. Okay. These are gonna be a little bit more intricate. Circles were the simple the simpler of all the graphs we're gonna talk about. So let's just kind of jump into an example to see what happens. Okay. So let's say that we have r equals 4 cosine 2 theta. Now I know it's a rose because it has that form. So you're going to have your notes available to look over. So I know it's a rose. So I'm going to just kind of do the same thing we were doing earlier, which is just plug in some values and see what happens. I'm going to start out with the easy values, 0, 90, 180, 270, 360. Okay. So let's go ahead and start out with that. So if I start out with 0, so if I plug in 0 here, 2 times 0 is 0. Cosine of 0 is 1. 1 times 4 is 4. So I'm going to go 4 units towards 0. Okay? All right. So now let's say I plug in pi over 2. So pi over 2. Pi over 2 times 2, that would be pi. Cosine of pi is -1. -1 times 4 is -4. So when I plug in pi over 2, which is up here, I need to go away from it 4 units. So 1, 2, 3, 4. All right. Now let's plug in pi. So plug in pi, cosine of 2 pi, but pi times 2 is 2 pi. Cosine of 2 pi is 1. 1 times 4 is 4, which means I'm going to go in this direction. 4 units in that direction. Okay. Now we're plugging in 3 pi over 2. 3 pi over 2 times 2 is 3 pi. The cosine of 3 pi would be negative 1. Negative 1 times 4 would be negative 4. So if I go towards 3 pi over 2, I need to go negative 4 units, which means I have to go away from it. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. Okay, so what it looks like now is like I have 4 corners here. So, I mean, this is called a row, so I can kind of guess what it looks like, but if we were to plug in a little bit more points, here's what would happen, guys. Remember how we initially started with this point right here, which was at 0, okay? Now, let's think of a nice value that we can plug in here. So let's say that we do pi over 4, right? So we do pi over 4 times 2, that would be 2 pi over 4, right? So at 2 pi over 4, that's pi over 2, and the cosine of pi over 2 is 0. So that means I would have to be right here. So what that means is it's probably going to go towards here, kind of like this. And then if you recall, after that, we had this point, I believe it was this point down here, but let's kind of verify, okay? In quadrant 2, if I put the equivalent of pi over 4, it's 3 pi over 4. So 3 pi over 4 times 2, that's 6 pi over 4, which is 3 pi over 2, which is also 0. And 0 times 0 would just be 0, which means that it puts us right back here. So what it's going to start looking like, guys, is basically you start graphing these rows, and it just basically looks like a bunch of petals as such. And I don't remember if this is going to be the exact direction that everything's doing, but at the end of the day, at this point, we don't really care about the direction of how it's graphing. We just care about the end product. Now, my drawing here doesn't look beautiful, but that's kind of what it looks like, right? It looks like what they call a rose. So you have what we call a petal. And we need to make some observations about it. So for example, I don't want to make this video super long, so I'm just going to go ahead and jump and tell you some of the data. The value here for, or A, would be what we call the petal length. So in our case, it was 4. So notice how each one of my petals is 4. So that's my petal length right here, from here to here, from here to here, from here to here, from here to here, right? Now, how do I know there's, I'm totally getting ahead of myself, but again, I don't want to make this video super long for you guys. N is going to tell you the number of petals. Now, you may be looking at me based on this example and be like, that doesn't make sense, because in our example, N equal 2 and A equals 4. So yeah, we're okay with that. We can see that. But N equals 2, which means if it's the number of petals, I see 4 petals. Well, that's because it has an exception. Okay? If N is even, then you have 2N petals. But if N is odd, then you have N petals. So in our case, we had an even number, so 2 times 2 is 4, and that's the reason that we have 4 petals. Okay? All right. So that talks about really what A does, what N does. Now let's talk about what cosine and sine does. Well, here's one trick that I can give you guys. All cosine roses have petal at theta equals 0. Okay, always. So you will start there. So how can you make this kind of fast? Okay, so I'm going to show you some tricks here. Okay, if you know that that's an angle where you have a petal, then you go ahead and draw a petal. Now, the other thing I need you to observe is notice how on this rose here we have 4 petals. The angle in between each is going to be congruent. So all of these angles are going to be the same. So what that means is the petals are equiangular, and I hope I'm saying that, which means they have the same angle in between. So here's what's going to happen. Let's go ahead and try one where we have an even and we have a cosine, and then I'm going to try to show you one with sine with an odd number of petals, so I can show you some things there. Okay, so let's say that you have R equals, and we're just going to totally make this up. Let's do -3, and let's do cosine 4 theta. Okay, so when we start our drawing, this is going to be very simple. There's a few things we need to identify. and that is how many petals and the length of the petal. Okay, now the negative here, once again, it's not really going to make much of a difference, guys. It's really just going to talk about the direction, which at this point in pre-cal we're not worried about. We'll talk about that in calculus for those of you taking it next year. So here's what I know. I know it has a length petal of 3, and I know that it has 8 petals. Now it's a cosine rose, so we talked about this. All cosine roses have a petal at 0, but if you don't believe me, you can try it. 0 times 4 is 0. Cosine of 0 is 1. 1 times 3 is negative 3, so it means at 0 we're at negative 3, which would give us a petal about right here. Okay? Now, here's where we're going to use our advantage of what we just learned. All petals are equiangular. Well, how many degrees or how many radians are there around a circle? Well, we know it's 2 pi for a full cycle, right? Now, if it's equiangular, that means we have to divide it by the amount of petals that we have. So if we have 8 petals, that means it's 2 pi divided by 8, which if we reduce that will be pi over 4. So that means that every pi over 4, there's going to be a petal. So pi over 4 is going to be about, right, if I go pi over 4, which is 45 degrees, that will be about here, and then here, here, and so on. So what's going to happen is I'm going to have a petal here, and I'm going to do my best to draw it, and then one here, and then here. That does not look like 3 there, and then I know I'm going to have one here, and I know I'm going to have one here, and then I got to have one in between, one in between, one in between. They're not going to be perfect. Look at that. I mean, that looks terrible. But as you can see, we have 8 petals. They're all equiangular, and I promise you that if you plug in values for theta, you will get every single petal that you have there. So that was that's some of the tricks that I would use if I were you for a cosine. Okay, now let's try something with sine. So let's say that we have r equals 4 sine of 3 theta. Okay, so nothing changes about the length petal and the number of petals. So in this case, we have a diameter of 4, and we have number of petals as, because this is odd, that means we have 3 petals. Okay, so here's what we're gonna do. We're gonna go ahead and try to figure this out real quick. So we're gonna plug in some values and see what happens. Okay, so if I plug in 0, 0 times 3 is 0. Sine of 0 is 0, so we get nothing, right? So we get a 0. Okay, if I plug in pi over 2, okay, so pi over 2. Pi over 2 times 3 is 3 pi over 2. The sine of 3 pi over 2 is negative 1. Negative 1 times 4 is negative 4. So when I plug in pi over 2, I need to go 4 units away from it because I got a negative. So that means I got to go 1, 2, 3, 4. The moment I know where one of the petals is, I'm good to go. So remember, all I need to know is where one of them is located. So I know that it's going to look maybe something like this. And I know I have 3 petals, and I know that it's 2 pi for entire revolution. So if it's equiangular, that means 2 pi over 3, which is 120 degrees, is where the next one is at. So if I go 120 degrees this way and 120 degrees that way, I'm going to be able to have the location of the other ones. Okay, so 2 pi over 3, right? So 2 pi over 3 from here, think about it. We're currently at 3 pi over 2, right? So 2 pi over 3 would be about where the pi over 3 is located here, which in our case is, let's say pi over 3 is about right there. So we're going to go, I'm going to do my best here. What was the length of it? It was 4, right? So 1, 2, 3, 4. I don't know. I'm going to go ahead and take a guess. About right there. And then 2 pi over 3 on this direction, that means we have 1/3 about right here, 1/3 about right here. So it's going to be, nope, hold on. Let's see. My apologies, not at pi over 3. That didn't make sense. It should be a pi over 6. Yeah, sorry. Make sure we talk about why it's pi over 6. And that's what I get for rushing. Think about it. You get 3 pi over 2, and you add 2 pi over 3. I need a common denominator here, so that would have to multiply this one by 3 and that one by 2. So that will be 9 pi over 6 plus 4 pi over 6. 9 plus 4 is 13 pi over 6. Which, remember, if it's just 2 pi, 13 pi over 6 would just be the pi over 6, and that makes more sense. Which means that if I add 120, or 2 pi over 3, that would have to be about right here. So that would be at the 5 pi over 6. Okay. Oh my god, that looks terrible. I'm sorry, guys. But if you do the mathematics, there is an angle of 2 pi over 3 right here. There is a difference of 2 pi over 3 here. And there is a difference of 2 pi over 3 here. Okay? So for sines, we're going to have to work a little harder. Unfortunately, they don't start. They don't start at 0. One thing I do want you to notice is that there are still some symmetry with respect to what we call theta equals pi over 2, or what you call y equals the y-axis. I'm sorry. So how can we do this? Because we kind of just plugged in values. What if we don't get lucky? Well, let's do one more example, and hopefully that'll help you out come up with another trait for roses. Okay, so let's say that you have r equals, I don't know, let's see, 3 sine of 5 theta. Okay, all right, so once again, we're going to go ahead and try to sketch this out. We know that the petals are 5 because that's odd, and the length is going to be 3. Now, I don't want to be guessing as to where it is, so here's what I know. I know the length of the petal. So what I'm going to do is I'm going to set this equal to the length of the petal. So it's going to require a little bit of knowledge from back in trigonometry. So 3 sine 5 theta is equal to 3. I divide both sides by 3, so that gives me sine of 5 theta is equal to 1. You can pretend that's u. You can let u equal 5 theta, which means the sine of u equals to 1. So now you just ask yourself, where on the unit circle is sine equal to 1? Well, sine is equal to 1 at pi over 2. Now, if you remember and you wanted to solve for every single one of them, when you do a multiple angle, you do a plus 2 pi n, but for our purposes, it's not necessary. Well, I wasn't dealing with you, so I want to go back and substitute that into for 5. So 5 theta. So now I'm going to solve for theta. I'm going to divide by 5, I'm sorry, which gives me pi over 10. So what that means is that I have a petal at pi over 10, and then if there's 5 petals, remember, full revolution is 2 pi, so if I divide it by 5, every 2 pi over 5. If I get the common denominator, that would be 4 pi over 10. So every 4 pi over 10, I would have a petal. Cool? Now, let's kind of go back here and see how we can kind of deal with that. Well, we know this is 0, and we know this is pi. If I make common denominators, that would be 10 pi over 10. Cool? So, what this means is that I'm dividing basically the entire top and the bottom into 10 equal parts, so it gives me an equal part of 20. Okay, so what that means is the following. If my first petal is at pi over 10 by algebra, and we know that the length petal is 3, again, you're going to have circles, so it's going to be a lot better for you. Let's say that pi over 10 is right here for me, and that right there is a radius of 3. Okay, now every 4 pi over 10, I'm going to have another one. So pi over 10 plus 4 pi over 10 is 5 pi over 10, which means that would be a pi over 2. So that would be a length of 3. So there's another one. Now, if I do 5 pi over 3 plus 4, that's 9 pi over 10. That's a little bit less than 10 pi, so it's going to be about right here. And remember, there's going to be some symmetry because it's sine. That makes sense. Cool? Now, I'm at 9 pi over 10. So I'm at 9 pi over 10. This one was 5 pi over 10. This was 5 pi over 10. If I add another 4 pi over 10, that's going to give me 13 pi over 10. Well, 13 pi over 10 is not going to be quite as close, but I'm just going to say about right here. 13 pi over 10. And if I add another 4 pi over 10, that'll be 17 pi over 10. Now, that would be about right here because of symmetry. And that'll be 17 pi over 10. If I add another 4 pi, that will give me 21 pi over 10, which gets me right back to this one, and so on. And there is my ugly looking rose petal there for you guys. Okay? I don't want to, again, make this video very long for you guys. So web assignment is going to be your opportunity for you to try. If you have questions as you're working with this and you get stuck, please don't hesitate to contact either myself, Mr. Holman, or Coach Otto with any questions. Okay? Now, we got to move on to our last piece, which is limicons. Now, limicons are not that difficult, but unfortunately, guys, there's a whole bunch of limicons. So let's first talk about the equation. So limicons have the equation of r equals a plus or minus b sine theta, or r equals a plus or minus b cosine theta. So once again, notice the pattern here, though we keep having sine and cosine, we're not going to deviate from that. There are graphs that deal with other trigonometric functions, but we're just not going to cover that in this class. Okay, so let's talk about a few things. I'm just going to go ahead and jump and tell you there's actually 4 types of limicons. Okay, and that's what makes this a little bit more difficult, or why students kind of dislike this specific graph. Okay, so here's what's going to matter. We're going to be looking at these values right here, and I'll tell you what they look like here in just a second. So if you do A divided by B, and we do the absolute value of it, okay, I don't care whether this is positive or negative, okay, if that is less than 1, then you're going to have something called a limison with an inner loop. And here's kind of what they look like. I pretty much call it the pretzel. So I'll give you an equation here in just a second, but let's say that you have something like that, and they're not very creative. It literally is a loop. Okay? So that happens if you have A divided by B and that happens to be less than 1. Okay? If you do the absolute value of A divided by B and that is actually equal to 1, then we have what we call a cardioid. And a cardioid is literally going to look like this. And you guys are going to be very familiar with it. It's going to be a very sharp turn. So it kind of looks like a heart, hence the word cardioid. Okay? If the absolute value of A divided by B is less than 2 but greater than 1, you have something called the dimpled. And what a dimple limison looks like, it's almost like a cardioid, guys. Here's the only difference, and this was I want to emphasize. With a cardioid, you do a very, very sharp turn. With a dimple, you do a very curvy turn. So very, very curvy. And I exaggerate them on the notes so you guys can see them. It almost looks like a bean. But basically, you make this very curvy versus that very sharp. Okay? And then the last one, let me go ahead and flip the page. It is going to be when you have the absolute value of A divided by B, and that is actually bigger than or equal to 2. And those look a little funny. They almost look like full circles, but they're not. So let's just kind of say that that's what you got going on. And you kind of start turning a little bit, and it starts to look a little flat up top. That's really what it looks like. Okay? It's not quite a circle, so it just kind of looks kind of flat up top. It just continues to turn, and that's what when we have a convex. Okay? So how are you going to do this? This is actually very, 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 very simple, and I promise you. First of all, you need to identify what type of limison you have, and then we're going to plug in 0, pi over 2, pi, 3 pi over 2 to make a decision. Okay? So let's say that we have r equals 3 plus 2 sine of theta. So we're going to take a look at this. We have 3 plus, we know it's a limison because it's in the form of a plus b sine theta. So now what type is it? So we have 3 divided by 2. Well, 3 divided by 2, the absolute value, it's less than 2, but is greater than 1. So according to our notes, if we have such thing, then we have something called a dimple. So all we got to do now is we're ready to kind of graph this. Now, recall that with circles I gave you some symmetry, and I kind of told you if it's a sine, you're going to be in the top or bottom. If it's a cosine, left and right. Well, if it's a sine, that's going to really help us out. But here's what happens, okay? I'm going to go ahead and use the strategy of just plugging in the angles, and then I'll show you some tricks. Sine of 0 is 0 times 2 is 0 plus 3 is 3. So at 0, I'm going to go 3 units on this way. Pi over 2. Sine of pi over 2 is it's just 1. 1 times 2 is 2 plus 3 is 5. So 1, 2, 3, 4, 5. So it's going to go 5 in that direction. Sine of pi is 0 plus 3 is 3. So 1, 2, 3. Sine of 3 pi over 2 is negative 1 times 2 is negative 2. 3 minus 2 is going to be 1. So it's going to be 1 unit here. So here's what it looks like. You got to be, these things are very, very rounded. So we're going to kind of make this very, very round. It's going to go this way. It's going to go that way. That is terrible. Sorry for my artistic abilities are not the greatest. So something like this. And what happens is we need to kind of go this way. And we know it's dimple. So I just gotta kind of turn around. And not very sharply, but I'm going to start turning. And that's terrible, but kind of what it looks like. Cool? So it's kind of very curvy here. I'm just going to make it like a little dimple. And that's about what it looks like. So it's kind of summarize what I did, right? First we identified it was dimple, then we plugged in 0, 90, 180, 270, to kind of get these points here, and you know the general shape, so you can kind of make an approximation of what it looks like. Another strategy some students like, and it's really up to you, it's I like to call it like a crisscross type of thing where you don't really have to think too much of it, but here's what happens, okay? If it's sine, it's going to be either top and bottom, right? If it's positive sign, it's going to be top heavy. I call it top heavy because most of it is on the top. And how do I know it's in the top? If this is positive. Okay, so what you do, once you figure out that this is top heavy, you do 3 plus 2, which is 5, so you go 5 units. And then you do 3 minus that, which is 1, and that's how you go down. Cool? Now, left and right, you literally are going to ignore this number, and you're always going to apply this number, so which in this case is 3, and as you can see, I went 3 units this way and 3 units that way. So let me go ahead and show you what I mean. So let's say that you have, I don't know, 4 minus 3 cosine theta. Okay, so we're going to identify the type of limison. We're going to apply the new technique, and you really choose what you like. You can either keep plugging in 0, pi over 2, pi, and 3 pi over 2, or you can try this new technique. So it's a limison. Now we got absolute value 4 divided by negative 3, which is 4/3, which is less than 2, which is greater than 1, which means it's still dimpled. Okay, so I'm going to use this new technique. Notice how it's cosine and it's negative. That tells me that it's going to be either left or right, but the fact that it's negative is going to be in the left, and it's going to be left heavy. So what I do is I actually add up those numbers. So 4 plus 3 is 7. So that means I'm going to go 1, 2, 3, 4, 5, 6, 7. That'll be a point right there. Cool? And on the opposite direction, I subtract them. 4 minus 3 would be 1, which would be right here. Cool? And then I'm going to ignore this, which means I'm going to go 4 up and 4 down. So 1, 2, 3, 4. 1, 2, 3, 4. Okay. Now let's say you don't like that technique. This is going to work with the angles as well. So let's go back. By plugging 0, cosine of 0 is 1. 1 times 3 is 3. 4 minus 3 is 1. There you go. Pi over 2. Cosine of pi over 2 is 0. Plus 4, 4. Cosine of pi is negative 1 times negative 3 is positive 3. Plus 4 is 7. 3 pi over 2, that gives us 0, 4. And it still gives you the exact same angles, whichever you like. Now, I know it's dimples, so once again, I'm going to make this, again, I kind of suck at drawing, but here we go. Make a dimple, here we go, here we go. And that is so bad. But anyways, that's kind of like the idea that you guys got going on. And this works for every single one of them. So I'm going to do one last example. We don't need to cover all 4 limisons. I think you guys can get the idea. Or I think I'm going to show you, just once you get your 4 points, just kind of make it look like, remember I kind of gave you the rough sketch strap of what they look like. Here's your inner loop, here's your cardioid, your dimple, we've already done 2 examples of that, and then your convex, okay? So I'm going to do one with an inner loop because typically that is what most students kind of struggle with a little bit. So let's say that we have something like, okay, remember to have an inner loop, A has to be smaller than B. So let's say that we have R equals 2 plus 4 sine theta. Okay, so that's A over B, which is 2 over 4, which in this case is going to be less than 1. So we have what we call an inner loop. Okay, now everything about this strategy is still the same, even though it's a completely different limison. You ready? Okay, so this is sine and it's positive. Sine positive means that it's going to be top heavy. So that means 4 plus 2 is 6. So 1, 2, 3, 4, 5, 6. Okay, I subtract these numbers. 2 plus 4 is negative 2. I'm sorry, 2 minus 4 is negative 2. So that's where it gets tricky. So it's negative 2. Well, don't forget that to plot numbers, so instead of going in this direction, I have to go 2. So that means I'm in here. It's like on the same direction, and we'll talk about that here in just a second. Now, left and right, I'm going to ignore that, and I'm going to go 2 units to the left and 2 units to the right. Okay, you don't like that. Once again, let's try it with angles. Sine of 0 is 0, plus 2 is 2, so that's why I get that point. Sine of pi over 2 is 1, times 4 is 4, plus 2 is 6, so that's why I get that point. Sine of pi is 0, plus 2 is 2, I get that point. Sine of 3 pi over 2 is negative 1, plus 4, times 4 is negative 1, plus 2 is negative 2, and that's the reason why at 3 pi over 2, I'm going away. So here's what it looks like. Okay, here's the body. Once again, this is not the difficult part, this is not the challenging part per se. Okay, when it's an inner loop, what you got to do is once you reach this point is you got to go towards the pole and you've actually got to cross it. You're going to go inside, you're going to go into that point that you plugged in, back to the pole and connect it, and that's how you're going to be able to graph your inner loop. Kind of looks like a pretzel type of thing there. Okay. I know I've been kind of rushing throughout this video. It's not the best lesson. I really wish I had more time to sit with you guys and practice a lot more of this. But I know that I'm already at 40 minutes. Watching a 40-minute video is very, very tough, very boring, and there's no way for me to give you breaks. I know I probably talked very slow for some of you guys. Maybe I talked fast for some of you guys. Please, please, please use the settings on YouTube to fast forward or slow down the video. You can rewatch whatever you need. Again, I am just an email away. Shoot me an email. Shoot Mr. Holman an email. Shoot me, Coach Otto an email. We are here to help you. This should give you, I think, a very good basis for you to try the WebAssign. I don't expect for you guys to have a lot of trouble, but if you do, please, please contact us, okay? That is all we have for you this week. Thank you for watching. Stay safe, and hopefully I'll hear back from you guys pretty soon.